Hello and welcome to lesson 1 of week 11. In this lesson, we are going to look at the graph data structure. My name is Mildred. Now, a graph data structure is a non-linear data structure. Just like we saw in last week's lesson, we looked at the tree data structure. Graph is such that it consists of vertices, which we call the nodes, and these vertices represent the entities in the graph, and then edges, which represent the connections or the relationships between the vertices. Now, we have the representation of a graph to be G. We have the vertices and the edges. Now these edges are just like a list of vertices or the list of adjacent vertices that we store, and whenever we want to create a representation of this, we can use like a dictionary where the key will be the vertex and the value will be a list of connected or of adjacent vertices. Alright, and we're going to implement that in this lesson. So we have this V as the set of vertices, and then we have this E as the set of edges connecting pairs of vertices. Now we have the different types of graphs. We have the directed graph, we call this the digraph, which have a direction. So when we have the edges like this, we have the edges have a direction. We can see an arrow pointing to from A to B. Then we have the undirected graph where the edges have no direction, and we have this like AB, and we just have this edge and there's no direction to it. Then we also have another one we call the weighted graph where the edges have weights, and this weight is like the cost, the distance, the time. So you see something like A, and maybe you see a number here, let's say 10, and then B. So that is a weighted graph. We're going to look at that later down in this week's lesson. And then we have the unweighted graph where all the edges have equal weights. We have a cyclic graph that contains at least one circle, and a cyclic graph, all this the dark, that contains no circle, and it's very important in things like scheduling. We have the connected and the disconnected graph, and a graph is connected if every vertex is reachable. And then we have the dense or sparse graph. Dense is when the number of edges is approximately the square of the number of vertices. So let's see how we can represent a graph in Python. We have the most common one, which is the adjacency list. We also have the matrix representation. Now the list is just like you have your vertex and then you have a list of connected vertices, and then we have the matrix, which is represented like this. Okay? So why do we use the list, which is the most common representation? It's because it's efficient for sparse graph, and then it's also easy to traverse, and it is dynamic. So we're going to implement the adjacency list. Now from all we have said, we want to create a class, and let's call this class graph. So let's say class graph. Now the init method will not have any parameter. You can think about this in a different way and implement it based on the way you think about it or the algorithm that you create. We want to store the graph in a dictionary where the key will be the vertex and then the value will be a list of adjacent vertices, right? So let's say self.graph will be equal to, let's make it an empty dictionary like this. So we are storing this as an adjacency list, because we'll have the vertex and a list of connected vertices. Now we have this. Let's create a method here that we can use to add a vertex to the graph. So let's say def add vertex, and we want to add the vertex, and let's call this vertex V. So the first thing we want to do is to check if this vertex is not already in this graph before we add it. So let's say if V not in self.graph, then we want to add this as the key, then graph V will be the key now. Also we'll say self.graph. Let's make this the key, graph V is equal to, then we'll put an empty list where we'll store all of the connected or adjacent vertices. Now we want to see how we can add an edge. The edge can be either directed or undirected, and so let's put a parameter, or let's put a property such that we can set the directed to true or false. So let's say the add edge, and let's put self. We want to add the first vertex, so let's say V1, the second vertex, and then we want to put, let's say, directed or to, let's set the default to false, and then we can set this to true in the future. So we want to say if the directed is set to true, then we add a directed edge from V1 to V2 in this code, so that we can use this code for both directed and undirected edge. So let's say self dot add vertex. So we want to add the vertex V1, we want to add the vertex V2. So we're using the previous method here because we are adding this vertex to the graph, and then we want to now set the edge for the vertex level. So let's say self.graph. Now we want to add the vertex, which is V1, self.graph V1.append. So after adding this vertex V1, right, so we add a vertex V1 here, the value will be a set of empty lists, and so that is the key in the dictionary. And so in that dictionary we want to use that V1, the vertex as the key, and we're going to append the values to that list. So we're appending V2. So why we're appending this is we're adding the key key will be the vertex, and then the value will be a list of adjacent vertices, right? So let's add just v1 and v2. Now let's put a condition when if this is not directed. Now we are putting this like directed is false, and we can set directed to true when we create an object of this class. But let's say if not directed. So if directed remains false, we want to say self.graph v2.append v1. Okay, so if it's not directed, there's no particular direction, so you have the other part. So like you see how we did it here, no direction A, B, so both directions, but when it's directed, it's just from A to B. And so when it's directed, it has the vertex v1, you append to that list that has this key v2, so it's directed. But if not directed, you put the second direction v2 to v1. Let's create a method that we can use to display this. Let's say the display and self. So let's say for node in graph, let's say for each node in the graph, we just want to print the node. So let's say print node, let's put an arrow and say self.graph node. So we're traversing through the graph and we're printing through. It's just like looping through a dictionary, but this is just for display. We want to display everything in the graph, the dictionary. But then we have different methods that we can use for traversal, and there are different types of traversal. And when we say traversal, we mean we want to visit the nodes in a particular order. Now we have different types. We have the breadth first search, BFS, which uses the queue, which is good for looking for shortest paths in an unweighted graph. And also we do it like the breadth first is a level by level traversal. Let's try to do that breadth first traversal. I'll do this outside of the class. Let's say I want to use the queue from the collections module, so import the queue. So we want to do this with the queue, and I'll create a method called breadth first search. I'll just do BFS, and I want to search the pass in the graph and the start. Now let's make sure when we traverse, we already take note of what we have visited. So let me create a variable here called visited, and I'll make this to be a set so we can have unique nodes. And let's dequeue here. So we'll say q is equal to dequeue. Then let's say while q, we want to say the node is equal to q dot. So we know q is first in first out, right? So let's say q dot pop left, and if node not in visited, print. Let's print node and let's append the end to be a space. End is equal to space, and then let's say visited dot add node. So what I'm doing here is I'm trying to traverse through level by level, and I want to take note of the nodes that have been visited, and I'll store it here in the visited. I store it as a set just so that it removes duplicate and we can easily just search that visited list or the visited set. Now we want to dequeue. When we dequeue, it means you are removing from the first, right from the beginning when you use queue, but we are using it from the collections module. We're using dequeue. So while we still have queue, right, while there are items to be traversed through, we want to say the node will be equal to, we'll use pop left so that we'll always get wherever we are on the iterator will become the node that we are working on. So if the node that we are has not been visited before, so we'll check it. If it's not been visited, we want to print out that node, and then if it has not been visited, we want to add it to the visited, because at this point now we have printed this out because we are traversing to just print out the result. Now let's say we want to also traverse. Let's look at all the neighbors of same node. So let's say for instance, I'll say for neighbor, let me just call it neighbor in graph node. So for neighbor in the list of the adjacent vertices, right, so the neighbor is the iterator. So for an item that is in that list of where this key points to, the lists of the values that this key points to, now we want to get if that iterator or the item pointed to by that iterator is not in visited, then we want to append it to the queue. So let's say queue dot append neighbor. Okay, so this should be able to traverse through level by level. That's the breadth first traversal. Let's try to create other traversal methods before we even test this. Now we want to have the second type of traversal here, which is the depth first traversal, and this uses stack, or you can also use recursion. It's good when you want to find a path, when you want to detect a circle, and maybe you will have topological sorting to do. So let's do depth first search like this. We want to pass in the graph, the node, and let's say visited, and we'll set a value of none. Now we say if visited is none, we want to create a set like this. Now we want to print out the node, and let's say end is equal to space. And then we want to add that node to the visited dot add node. So we'll do the same thing here like for neighbor in the node. If the neighbor is not in visited, we want to now recursively call this function. So let me copy this, and we want to use depth first traversal. I will say for neighbor in graph graph node. If neighbor not in visited, then I want to recursively call that. I'll say DFS graph neighbor and then visited. Okay, so in this recursive call here, I'll pass in the graph, I'll pass in the node, now will be the neighbor, and then I'll pass in whatever the value of visited is, or the visited set, so that we can use this recursively until it traverses through this completely. So this is like doing the recursive method. We can also create an iterative method. Let's try iterative. Let's say the DFS iterative, and for this iterative we'll just pass in the graph and then the start. Now let's say the visited will equal to the set that, and we want to put a tag will be equal to a list of the stats. Then let's say while stack node is equal to stack.pop. So we are the node is going to be the topmost now because we're using stack, right? So it's for stack, it's last in first out. So the node is stack.pop, and then if the node is not in the visited, we want to print out that node, and let's put a space at the end. Then let's say visited.add, we add a node to the visited set, and then we want to do the same thing with the neighbor, but now we're going to just append to the stack instead of calling it iteratively here. So I'll show you how we change this. So let's say for neighbor in, let's reverse the node. So let's say in, because now we are doing from the, for stack is last in first out, right? So let's reverse. So let's say for neighbor in reverse graph node, if neighbor is not in visited, and then let's now append, let's say start.append, because a stack is like a list in Python, so we append that neighbor. So this will give us like the stack or the iterative approach to the depth first search. Now let's try to test this. Then we're going to look at how we can do circle detection in graph. Or let's just go straight to the circle detection first before we test this, so we can see everything. Now when we talk about circle detection, we can detect the circle in undirected graph when we visit an already visited node and that node is not the parent of the current node. So let's say in an undirected graph, we want to detect the circle to say, let's use something that will return a boolean whether it has a circle or not. Let's say def has circle, and let's call this undirected, so we can create a directed graph. When we pass in the graph, and let's take note of the visited nodes. So visited be a set, and here let's create another method within this method. So let's say the def first search here, the node and parent. So we want to just detect the circle here, and the circle will be when we revisit an already visited node or that node is not the parent of the current node. So we want to get that parent. Let's get the node and the parent, and let's say visited.add the node, and then check the other vertices here, the value. So say graph node, if neighbor not in visited, we'll say if DFS neighbor. So if we want to check if it has a circle, right, and we are doing this method or this function for an undirected graph, and so we want to create a function within this function that will help us look through this, the node and the parent. So we'll say if DFS neighbor node, then let's return true, which means that it has a circle or it detected a circle, and then we use elif here, and here we want to say if the neighbor is not the parent, right? If the neighbor is not equal to parent, we want to say this circle is detected, so we return true, and then if none of this is the case, let's just return false, so no circle detected here. And then let's now look within the outer function for the has circle. So all of this is within the inner function, right? And so for the outer function, I'm going to say for the vertex in graph, if the vertex is not in the visited set, and if the, let's do a traversal, so let's traverse is if DFS vertex none, then we return true, and if not, at the end we just return false. I think that should do it. So this is when we want to detect a circle in an undirected graph. Let's try it for a directed graph, and this one will use the depth search, and we'll also use a recursion stack. Let's try this one so we can test all. So we'll say def has circle, and let's call this directed. Now we just pass in the graph, and we want to create an empty set to store all of the visited nodes. We also want to get a stack, so let's call this, and we'll make this an empty set also. Now we want to create an inner function. We'll call this depth first search, and we pass in the node. Let's say visited.add that node and recstack.add. So this recstack is just like we are creating. The recstack is the recursion stack that we want to use. We want to use the depth first search and recursion stack also. So now let's do the neighbor part. Let's say for neighbor in graph node, if the neighbor is not in visited, we want want to use recursion, call the function again, neighbor, dfs neighbor, we return true, which means a circle is detected, and let's say elif neighbor in recursion stack, then you also return true because a circle is detected. But if not, at the end, so if it is in the recursion stack, so here let's remove it, return true, and then let's remove it. So let's say recursion stack dot remove node, and we now want to return false if it is not there. Now let's use this. Let's say for vertex in graph, if vertex is not visited, if TFS vertex, we want to return true, else we return false. So I think that this should work. Let's try to test this, and then I'll explain it again before we go. So we'll say if name, so let's create an object graph, and we want to say graph dot add, let's add an edge. So let's see the methods we have. So we have add vertex and we have add edge. So let's add the edge here. So let's say graph dot add edge. This add vertex, we're not going to call it directly. It's when we add the edge, then we'll add the vertices to the edge, because we'll use this add vertex method here to call this and add the edge. So let's just use the add edge. So we'll say add edge. Let's add an edge. Let's say the vertex here will be A, and let's do that. Let's do several. I'll copy this. I'll just put A and let's say C, and let's do, let me put B and D. Let me put C and D. Let's say T and E. Let's stop here. So the add edge method here, when we do that, we supply the vertex 1 and vertex 2, and then we'll leave the directed set to false as it is. We can put the value for directed equal to true if we want, but since we have an initial value and we want it to be an undirected, we'll leave it like this. Let's print the graph. I'll say print graph. Let's use the display g dot, because we use this display to just loop through the dictionary here. So let me run this. Let's see the graph. So we have the graph, and what we are doing here is a directed graph like this. The directed graph is what I just did here. So we have A, then we have the adjacent list vertices here, B and C, because what I did here was I added A has, the edge A has B, the edge A has C. So we just have a list of B and C. Now B, we have D for B, and let's see, B here has A also, the adjacent vertex A. So B here has A and D. So we'll look at C here. C has D, here C has A. So we have C here, A and D. Then we'll look at D. When we added the edge D, we can see D has E, we see D here has C, we have D here has B. So we can have D as a vertex, and all of the adjacent vertices will be B, C, D. I mean B, C, E. And then for E, we already have D here, so we can see how it's printed out there. So we see the list here. Let's say we want to print out, let's do the breadth first search. Let's do from A, and let's do a traversal from A. Let me do something here and say print, use \n, so it starts on a new line, and I'll say breadth first search from A, and for this I'll just use the function breadth first search. I think that's what we created here, breadth first search here, and then we'll pass in the graph, which is G. So we'll say G dot graph, and we want to pass in A because we want the breadth first search, we want to start from A, and here we'll pass in both the graph and the start position. So we'll say from A. So let's run this, and we'll have breadth first search from A, and this is a level by level. So we'll see from A we have B, C, D, E. So when we do the breadth first from A, here we have from A, B, C, from A, D, and then we have E, like that, because it's just unique values we are getting. If we want to do depth first from A, let's do that. So let's do depth first search. I'll run this, and then depth first search from A, B, D, C, E. So you see that the breadth first is level by level, and this A, B, D, C, E. You can see that A, B, C, and then from A we have D, and then we have E. Okay, let's look at the iterative one here. Let's do the iterative here. Let's say DFS iterative. Well, let me just use this. So the function name is iterative, and we start that from A. We have that the same thing in the iterative, and let's try to see if we detect a circle here. So in undirected graph, let's say I'll say print, let's say print has circle, and I'll call the function has circle undirected, and the graph is g.graph, and I want to do the same thing for the directed circle. So let's run this, and then we have has circle in the a undirected graph, true. Heart circle directed, true. Alright, so these are the different ways. In our live web conference, we are going to look at labs and different ways to understand this deeper. I know that in this explanation you won't really get a detail, and that's the importance of attending the live class. And this is just to introduce you to the graph data structure, and then when we do real world application and app building from this, you will understand it deeper. And some of the applications that we can do with this is social networks, when we want to see friend connections, the way we build our social media apps, the graph data structure. When we want like Google Maps for the navigation system uses the graph data structure. Like we want to use routers and paths like in a computer networks. If you want to use recommendation engines, you want to build a job scheduling, maybe web pages and their links like a Google page rank, and maybe circle the design, family trees, or you want to have things like course prerequisites, just a list like that, or all those kind of apps. That is the advantage or the application of graphs in the different apps. So this is where we end this lesson. Thank you and see you in the next lesson.